I think we can start now. So welcome to our, I can't remember how many we've got to now, but our Blue Skies Greener Future webinar series. Today we're going to have Justin Perry, who's going to be talking about the future of the chemical sector, which future the chemical sector. I'm just going to give just take a minute or two to introduce our Transforming Foundation Industries Network Plus. I'm Ian Rainey. I'm the director of the Transforming Foundation Industries Network Plus. And these are my colleagues who are involved in the running of the network. Of course, myself. Then we have the Deputy Director, Susan Bernal-Lopez from the University of Leeds, Bill Sampson, who is here from the University of Manchester, and Cameron Bridle-Pierce. We're in the process of allocating our Independent Advisory Panel chair. Previously it was Chris MacDonald, but we change this each year, and we're having a new one confirmed by the end of this month. You've been dealing very much with Deborah Foggart, our marketing officer, who handles such events and the advertising and all manner of marvelous things to do with making us visible online. And our network manager is Neil Lowry. Bit of background: the core aim of the Transforming Foundation Industry Network Plus is to identify and co-create with the foundation industry's new science and technology that enable transformation towards more sustainable, cost-efficient products and practices. We have multiple themes: resource efficiency, next generation processes, energy efficiency, and we also go towards more humanities type activities in policy and advocacy and equality, diversity, inclusion. We're charged with trying to create a more diverse foundation industry as we move forward with our grant. We're up to about 500 or so members. It's about a 60-40 split in academic to industrial. We fund projects. So we've funded now about 500K of projects. We do feasibility studies up to 6 months in length. That's about 12 projects so far. But at the end of this month, we will announce another 6 or 7 projects, I think, based on a call that was recently completed. We have another call coming out dedicated towards early career researchers. Please watch this space. It's not finalized yet, but it will be appearing probably in early May. And it's all about getting postdoctoral researchers within the United Kingdom to interact more with the foundation industries. So it's focused on effectively PDRA people. It's an open call in the sense that any topic that is within the remit of our network is viable for submission. So please watch out for this. We are very, very keen to engage with the younger researcher within the United Kingdom and encourage them to put in projects that are focused on helping the foundation industries transform. I've said all of the things I'm going to say, so I'm going to stop sharing my screen, and I'm going to ask Justin to share his screen and then begin his presentation, which is much more exciting than me talking.
Right, no, that's not the wrong one, isn't it? I've done the wrong one now, haven't I?
I can see your...
Right. Is that the...
It's good, Justin.
That's good. Right. Super. Right. Thank you very much for the invitation, Ian, and the TFI Network Plus. Okay, so my lecture here, what future for the chemical sector? Okay, so a bit of a plan of what I want to talk about. First of all, where we are now, then which future do we think? Now, looking at this from a very academic perspective, I've chosen 3 different ways of thinking about the future going forward. And hopefully I'll convince you that actually what we need is not one of these, but all of these and more, because I'm very aware that I don't know everything about the chemical sector, and I'm not sure that there is anybody who does. So it really has to be more handed. It has to be a whole array of people pushing this forward. And then the final part, whichever future, what we need to do now, and that's just stuff that I think we need to think about if we're going to get any of these things working. I should say all views expressed are my own and on my own idiocy. They're not part of what my university thinks, or my university, my research collaborators. I have checked with them. I think they agreed. We said, all my funders, these are my own ideas, and please challenge them at the end. I do appreciate people telling me I've got things wrong if I've got things wrong, so please do. So first of all, I think you need to know who I am, then you can work out where I'm standing. I intercepted Ian and told him that instead of him telling people who I was, it might be better if I did it rather than he did it. I have a very straightforward chemistry background, undergraduate degree in chemistry from Cambridge, PhD in chemistry from Trinity College Dublin, and then I was a postdoc for 4 years at Durham. But since 2000, I've been at Northumbria University, which is the other university in Newcastle upon Tyne. I've been there 20-something years, and basically my entire interest in that time has been on answering and looking at interesting, knotty questions in chemistry. And a lot of those have been in collaboration with industry. So this is how this is how I'd like to think I have an idea of where we could go forward on this. So just in terms of my background, in terms of research interests, from about 2006, alongside my colleague Gary Black, who's professor of biochemistry here, I ran a university service, never actually spun out, called the Enzymics Biocatalysis, where we did contract and collaborative research for anyone who is interested, really, which is principally the pharma and chemicals industry. So that was really very interesting. So you'll see some of my topics are really about how biotechnology and chemistry could come together and produce some amazing stuff. More recently, my interest in polymers has led to me and my colleague, Dr. Matt Unthank, having another university service called SPIN, Synthesis and Polymer Innovation at Northumbria. And that's our service doing polymer chemistry and at the sort of interface between research and research and development, and then in more industrial sense. Over this time, who my funders been? Well, I get funded by the usual sort of people, but possibly unusually for an academic, I have done a lot of industry collaborations. I've had a long relationship with AkzoNobel, or International Paints as they were, or Cortels before that, who have a very large R&D centre just outside Newcastle. And then I've been embedded to some extent using the KTP scheme, which is an amazing scheme. If you're a company person, I recommend you look at that as a way to interact with industry, interact with universities. And I've done it with a whole range of companies. So Multichem, are an ink and paint company, Quantum DX, medical diagnostics, Lear Corporation, big corporation, but we were looking at polymers in car seats, Sterling Pharma, pharmaceutical company, and Ideal Manufacturing, our laundry business. In terms of more about sort of the future of the chemical industry, there's two things that possibly make me slightly qualified for this. I've had two EPSRC grants as a co-I. One was part of the New Industrial Systems grant, New Industrial Systems program, where we have one called Immortal Manufacturing. The other ones in the thing were funded in this round were called Chatty Factories and Optimizing New Manufacturing Systems. So we were forced to have some really quite exciting titles. So I do worry about going to an industry event and talking about a project called Immortal Manufacturing, because it does sound like it opens many doors. But effectively, the idea was in this particular scheme was to go, a whole load of academics were put up in a hotel for a week, and we had to work out what we thought the manufacturing systems would be in the UK between 2030 and 2050. And this is what we came up with. Immortal Manufacturing was embedding biotechnology within chemistry, within manufacturing, within engineering. It's very interesting. Anyway, so I'll talk a little bit about that. More recently, since that one's finished, I've become part of the Transforming the Foundations Industries R&I Hub, which is called Transfire, which is led by Mark Jolly out of Cranfield, and myself and Matt, who I mentioned in terms of spin before, are the bulk chemicals national co-leads in that. So, and that's really interesting. It's a sort of sister organisation to what Ian leads here, and there's quite a lot of collaboration, crosstalk between the two in terms of working together. So very exciting in terms of the interface between universities, industry, and funding. Everybody likes. Right, that's enough about me. Let's talk about the topic, the future of the chemical industry. So the first thing I did, and this was I did as part of my role in Transfire, was to have a look at the sort of chemical parts of the sort of foundation industry road mapping. There's quite a lot of road mapping going on. Obviously, quite a lot of it is suffers. The early stuff suffers from the fact that no one saw Brexit coming, and then the later stuff suffers from the fact that we've just had COVID, or we still have COVID. But there are some really interesting insights in there, and I hope I've distilled out some things in the next few slides, which could be interesting. So in terms of this, obviously, chemistry, whilst it's not often at the same sort of temperatures as things like glass and metal, in terms of heat, it is still energy intensive because of all the processes, and as a result, it's really also under pressure because of the sort of carbon emissions. And this is something that's, I wrote this line 4 months ago for another presentation. The UK is seen as an expensive country for energy, but oh my word, is that true now? Obviously, so that's that's something that is a big thing on people's radar. Something that I've seen as an academic, when you go in and talk to people, you're not talking like colleagues who might be working in software. When you're talking to somebody in chemistry, there are high capital costs, big things, big pieces of capital equipment. Plants are massive, they require big resource, and as a result, rate of change tends to be quite slow. And the majority of the industry at the large, for larger bits, are large companies. And whilst, as I said, names may change, the sites remain the same. So, obviously I'm based in the Northeast, and there's been a lot of flux in terms of the names of various companies operating sites, but the sites are still there doing similar sorts of stuff. The other thing that's a bit different in the chemical industry is it's driven, as I say, driven by multiple business-to-business transactions. I mean, one of the interesting things that I saw in some of these roadmaps was that actually chemicals move around. Very few chemicals from the beginning to the end user are done by one company. People move things around, and that number there, chemical sector has an average of 40% imported components in its exports. Things are moving around. It's global, truly global. And as a result, chemistry is not vertically integrated. So the person at the beginning is unlikely to be selling to the final customer. And that, I think, has a little bit of an issue in terms of moving things through. And I'll talk about that a bit more later on. So in terms of the drivers, as I said, carbon legislation is a major driver in all this, and whether it's atoms or joules, as I said at the end there. The existing technology, well, the good thing is that we've got petrochemicals to work with at the moment as our basis for everything. And the good thing is that's really quite well optimized. But the problem is any alternative technology immediately has to compete with something that is working really very well in terms of economics and efficiency. So as in anything, if change is not immediately better, it's very difficult to suggest to someone that they should be doing something different. Strong driver is environmental health and safety REACH legislation, which is interesting and can be one of the ways to suggest how things can be done differently. And as I said, the final thing is, what's the main focus for saving? Is it atoms or joules? And actually, this is a big discussion that we have in Transfire, the R&I hub that I'm part of. I mean, lots of companies are talking about, from the other foundation industries, it's all about saving energy. Well, the chemical industry is very energy intensive, but a lot of the time people want to talk about reusing atoms, what's a byproduct, how can you use a byproduct? So there's an essential tension there. And obviously there's no reason why you can't do both, but to a certain extent, there has to be some sort of focus on what is the improvements which are required. I did pull out some items of good news in these roadmaps, which is quite interesting, really. I mean, you hear a lot of doom and gloom. Certainly, if you work in a university, we tend to be sometimes quite negative about things, and I do try and fight against that. But UK chemicals industry sector grew 27% between 97 and 2016. Obviously, that data is very well chosen for the various things that could possibly have sorted that out. And indeed, the UK chemical sector, and this is something I tell to the students, chemical sector is really good at productivity improvements and energy efficiency. It does do this very well indeed. So productivity has shot up over the similar time as well, which is what you'd expect with people putting R&D in. And in fact, there is a strong R&D culture in the UK, according to the roadmaps, and I would agree in terms of putting money in. And whether that's R&D in terms of people or investment in large kit, that seems to be there. So my three take-home messages from this would be that, we tend to be on the up in terms of the industry here. We tend to have an appetite to do things differently, and we have industry, thankfully, is one that is interested in looking at new novel innovations. And that, as an academic, that's very interesting as well. So what future shall we aim for? Right, so I think the thing to say is I've got three different futures, and they're three different emphases of the same thing. So the first thing I've got here is words with the prefix RE, so reuse, recycle, that sort of thing. And obviously this is a big part of the future for the chemical industry, because we don't want to be wasting atoms. You can't waste an atom, to be honest. And to be honest, the foundation industry is one of the most efficient industries in terms of that, the chemical bulk sector. I mean, if you look at the amount of waste per gram for the foundation industry, it's tiny in comparison to things like pharmaceuticals, which admittedly do some quite complicated chemistry, but tend to use quite a lot of extras, which are part of the final product at the end. So there is quite a lot of interest in being as efficient as possible, reusing stuff. This GIF on the side here is in fact something that was on holiday in Germany, and my children really enjoyed the fact that you could bring stuff back. Your PET bottles and your tin bottles, you bring it back to Lidl, you feed it into the machine, and it scans it, has a look, and gets money back. And my point putting that, wouldn't that be lovely if everything could be on that basis? But it's straightforward in some things, and once again we have discussions around glass bottles and sort of pieces of metal. That's relatively easy to recycle, and as a result, those things have very good recycling routes through at the moment, which is very efficient and historically have been amazing. And paper, for instance, paper is a really well recycled resource. Chemicals are so much more difficult because they are so diverse. But that doesn't mean it's impossible. It's going to be more complicated to do. And to a certain extent, this is why we need to think more deeply about this in terms of how we can do it, and in terms of how we can actually move things through a system where actually the bulk amounts of different chemicals might be tiny, but might be useful. So there might be smaller volumes, but more valuable volumes. And the only way to do this is industrial symbiosis. Working out who's got what, who needs it. And to be honest, I think that's an IT task which each company can move into. But I talk a little bit more about that at the end. But yeah, reuse, recycling is definitely where we're at, and everybody's interested in that. Now, one of the things that myself and Matt, who's my co-researcher in terms of the polymer science at Northumbria, one of the things that we've looked with, and this has been part of what we do at Transfire, is we've been looking at PET flake. Now everybody looks at PET flake, but everyone looks at the nice PET flake. If you're a recycler, a large proportion of it goes back into bottles, but every time someone puts a bottle in and doesn't take the cap off, what you get is a situation where that cap can get ground up into little bits and it goes in the flake, and then that's a flake that's less valuable and people don't want. Or it may be something that goes into a meat tray, and the PET in a meat tray is much poorer quality than a bottle. So if you talk to the recyclers, they have a lot of bad PET that they need for some other reason, and we've been thinking, well, what can you do with that? And one of the things that, you know, Matt has spent some years as an Axon and Bell coatings expert, and I've worked with him for many years. And, you know, we tend to think about coatings a little bit in terms of a way to recycle, or I should say reuse materials. You know, sort of things like on a pipeline where you need a really robust material, and you can make it strong. Well, one of the things we thought was, well, if you can take this PET mix flake and use some biosourced components, and use the PET flake to offer the really strong coating hardness that you need, you can make a PET alkyd coating. So we've been working on that, and it looks pretty nice. So that coating on a steel plate is one of ours, and it does have the sort of things, you know, sort of the solvent resistance that would be of interest to people. So, you know, we've got a method for that as well. So reusing polymers that aren't recycled. There are plenty of things out there being recycled. It's finding uses of things which aren't quite there. Okay, so one of the other sort of recycling challenges that industry has, and I can see people coming at this from all sorts of angles, and, you know, it's a good challenge to have, I think, is sort of the really large, high-tech, hard thermosets. You know, not every plastic can be, you know, broken down as easily as a thermoplastic. We can melt it and reform it into something else, or clean it up, because it's a relatively straightforward way to break down the linkages. There are lots of lovely companies out there who are saying, well, we'll just take this stuff and do some exciting scaled chemistry and turn it into syngas and then feed it back in. And that's brilliant. I think that's, you know, that's obviously one of the strands of what we've got to do here. But at the same time, we've got to think about, you know, are there alternative uses? These images here, if you look at wind turbines have to have very light, very strong turbine blades, which you just do not want to be fixing in the middle of the North Sea in winter time, when they're, you want to put them out there and last 20 years. As a result, they are the most robust things ever. And currently we have a situation where, you know, what we're going to do with them. There were one of the numbers I saw, there's a quarter of a million tons of these things already. We have an issue, what are we going to do with them? So some issues here, people are using them as whole objects, quite like that. There's a Danish bike shelter, which looks pretty nice. And then there's obviously lots of people have seen these Dutch parks where they're taking some of these blades. I have to say, having shown these to my children, they did point out that all the interesting pieces of that park were not part of the turbine blades, but actually extras. So maybe that's not something to do. But I mean, can we use this material for another purpose? Okay, so is it a case of this, you know, these sorts of hardcore thermosets, can we use them in a different way as a filler, as well as breaking them down? So I think that's a challenge. Is there a way to repurpose them as small particles? Because filler is an important part of our life. If you look at coatings and paints and pigments, filler is an important thing that gives material properties. So another aspect of it is, if we're doing polymers, can we do polymers which are more functional? So if you've got a polymer on a wind turbine, can you have a situation where that turbine is actually, if it suffers a crack, it can actually heal itself, or something like that? And this is one of the things in Immortal Manufacturing, and hence the name, was we were asked to look at avoiding recycling by having a more circular way of doing these things with healing, self-healing. So video, yes, hopefully this will work for you. It worked for us earlier on. So this was one of the polyurethanes that my group worked with, and it's a slightly ugly looking plastic, but it's sort of stretchy. And then Brad, who was the person who worked on this project for the latter half of it, he cuts it. Don't worry, he doesn't cut his fingers. It does look like he's going to do that. You can pull it apart. You get the blunt ends, and you can put it back together again. Push together, and it's sort of like it does stick together. So I should add, the outside of the plastic is not sticky. It's just where it cuts that it sticks. We get a lovely bit here where it time speeds forwards for a bit, and then basically we can tug on it. It stays together. So I mean, we had companies interested in this in terms of coatings for cables in inaccessible areas. And that's the sort of use case we're thinking about. You know, if there's a situation where you can put a little bit of pressure and push things back together and still get stuff like insulation, that's quite a useful idea. So, and that particular plastic, you know, you can it retains a good proportion of its strength afterwards. It's not 100%, but we got up to 67% of its mechanical strength afterwards. Just one of the self-healing ones. I'll talk about another more sort of biotechnological one in a minute. Okay, so yes, you could, so self-healing things, if we could have more a longer lifetime for things, it might be better than creating polymers which, once they're broken, are well broken. Another thing that's of interest, obviously, and we're not the only people, this is a big thing. Can you have more expensive polymers which are built to be recycled? So once again, you know, thinking about wind turbine blades, can you have a thermoset that is really, really rigid, but under a very tight set of conditions, ones that you don't come across in the North Sea in a cold January night, which will make it fall apart? So this is a really good idea. The good thing about that is that you'll have the situation where you might be able to have a polymer which has a resale value. If you can go back from thermoset to components relatively straightforwardly and purified, then you could build a recycling chain for something like that. I think that's an important thing that we have to think about here. Can we build a recycling chain for polymer components, because that's required? Okay, so one of the things in Transfire do is I get to talk to social scientists a lot, and that's great. They introduced me to this term dematerialisation, and that's really interesting. I spent some time thinking about Star Trek, but it's nothing to do with that. It's the concept of using less of everything, okay? And if you use less of something because it works particularly well, then there's less needs for recycling. And I think this is a really interesting concept. I mean, I'm illustrating it through my simple mind by a pair of shoes. There's a pair of shoes at the bottom that my dad bought in 1960, which, as you can see, he's had repaired several times. And they work very well. And then also you think about trainers, and that's the latest pair of trainers. You cannot repair trainers. So, but you know, you think about the amount of waste. Now, obviously, I have to say, people who are making trainers are working on that. They are one of the people pushing for recycling of things, but at the moment, it's a huge problem. So dematerialisation as a concept would suggest that, can we find a way for a particular thing to be used better for longer and not have to keep pushing it around the loop of being recycled? I think one of the things that we have a problem in chemistry is that quite a lot of the chemical industry doesn't ever see its customer, its final eventual customer. And, you know, there's, you know, if you make methyl methacrylate, you know, someone telling you should be selling less of it seems to be sort of counterintuitive to your business model. But I leave that to our colleagues in business and social science to work out how we get around that particular thing. But in my mind as a chemist, I think this says to me, we could support more expensive materials if we did this, because people would pay for a longer life. Okay, on to the second thing, biosourcing. This is something that is, you know, obviously a good idea. We're going to have to move away from fossil feedstocks. Fossil feedstocks are very good. They've made the world a better place, undoubtedly. Very available, very predictable, and we have the infrastructure to convert a continuous supply out of holes into the ground into lots of lovely things. And sadly, biological sources, biosources, are very rarely like that, and that's a problem. I mean, if you think about some of the most available biosources of material, things like cellulose and chitin and lignin, you know, they're not nice liquids. They're not nicely constrained into their physical properties. They vary over the year. In their availability and their constitution, and it really matters where you get it from. So this makes it all very difficult. And then another, I mean, and I've talked to other people about going, well, we could just get bacteria and fungi to make stuff for us. Well, you've got to think that those things have to eat too. They're not just sucking the, you know, they're just not making carbon out of nowhere. Where's that going to come from? And obviously, lots of people say carbon dioxide, and that looks like a good answer. Okay, so carbon dioxide is a source of carbon is good. Okay. The other thing that is important, and I say this to students when I lecture them in final year, and they're trying to work out what they want to do, I say, well, look at what the difference is between fossil feedstocks and biosourced feedstocks are. You know, the stuff that comes out of the hole in the ground, hydrocarbons, it's made of hydrogen and carbon, and then you look at the sort of the cellulose, this chitosan, the lignin. You know, they tend to have lots of oxygens in them. You know, 2 of those are polysaccharides. They are very oxidized sort of stuff. And if you look at the catalog chemicals, commodity chemicals, they're somewhere between the two. So all that chemistry, bulk chemistry, where people have gone from hydrocarbons and oxidizing stuff, is going to have to change to some extent. If we're going to start using cellulose, we're going to have to go the other way. So it's from the world of oxidation to the world of reduction and removing functional groups. So there's a bit of a thought change there. Okay, so things that you have to deal with in terms of the variability in sort of biosourced things. Well, first of all, different ways of separating. As I said, a lot of these things are quite difficult to work with, and you know, I've got plenty of experience of that. One thing I propose, which we're interested in people to think about, is quite a lot of the problems which come from these things would be if we classified chemicals that we weren't sure of exactly what the chemical nature of them was entirely, to the level of the small molecules. If we class them by their use case and their physical properties rather than chemical structure, it would mean a different way of regulating these things and thinking about them, but it might mean that we get a quicker way to adopt these things. So for instance, I mean, I see this a little bit, I do some work on chitosan, which is one of the polysaccharides, which is completely unused, well, relatively completely unused in the marketplace, I think I'll say. It's sold on the basis of the viscosity of it in an acid solution. Why? Because it's really difficult to tell the molecular weight of these things. Okay, that sort of way of thinking about materials, is that a way forward for some of the more complex biosourced materials, which would have a use later on? Okay, so one. The other thing is, obviously, if we're using biosourced things, we should use biocatalysis and biotransformation to use them, because nature has many years worth of experience doing this sort of thing. So I've got some experience of that, and it's magical. So for instance, here's an example. Paul Race was the molecular biologist on the Immortal Manufacturing project, and this is some slide material that he's provided with me. You know, if you look at erythromycin in the middle, that microorganism on the left there can make 1 gram per litre per day of that stuff, but the original total synthesis of that took 52 steps with a horrendously small net yield. So, you know, biotechnology can make complicated stuff quite easily. Okay, now I know that that's not a great yield for the chemical industry. You do like a much higher yield, and that's obviously, you know, one of the things we have to do. But biocatalysis is being adopted at scale, and people will know that. So for instance, Mitsubishi, BASF and Lonza are companies which are using this on scale. The big poster child for biocatalysis at scale is making acrylamide from acrylonitrile using nitrile hydratase, which is an enzyme I've worked on. An amazing thing. It sees nitriles and converts them solely to primary amides, not acids, not carboxylic acids at all, and it does it at neutral pH. It does it very well indeed. And you know, and you can find versions of it which will work on other things. So you can make nicotinamide as well. So that's a big tonnage item as well. So you know, that's something that's used on a large scale. I mean, the other thing that is coming through, a pharmaceutical industry uses this all the time, is carbon R reductase. These enzymes are absolutely amazing things. They will convert carbon R to an alcohol, and they do it beautifully. You can see that the fuel for the reduction is glucose, which is just very available as well. So nice and clean, no horrible metals, and the word security of supply there is quite easy, because you've got an enzyme, and enzymes can be grown up relatively straightforwardly. You don't have to worry about sources of metal or that sort of stuff. That's an example of an enzyme which is moving through industry at the moment. Certainly it's great. And obviously you've got all sorts of extra things that you could possibly say in terms of chirality and that. I know that's not important for everyone, but it's a nice added benefit that you can have. I think one of the things I need to say, this is from my history of talking to the chemical industry about biotechnology, is how can you make an enzyme? And actually it is, once upon a time, it sounded like black magic when I started talking to chemists and chemical engineers with my colleague Gary 15, 20 years ago. People say, oh, this is impossible. I know people who spent the entire PhD working on one enzyme. Well, it wasn't that difficult 15 years ago, and now it really is a commodity business, which is one of the reasons we do less of it in the university now in terms of selling enzymes. And literally, as this flow chart says, you start off with an enzyme sequence, which you could, from an organism you never meet, from a database you can find online, and you can prune it, make it, change it, and then you can get the DNA made chemically, and then you can put it in a host system, which you can buy from a supplier, and then a fermentation expert can make as much of it as you like. So genuinely, this is how it works. You've got to find the right enzyme, and that's where the skill comes. But actually going from enzyme through to, enzyme sequence to enzyme, so that chemical catalyst or reagent is something that can be done, and done in a large scale as well. So I'm hugely keen on it. This is one of the sort of experiments, that one of the projects that we did, funded by Innovate UK, feasibility study and then a CR&D funding, with David Randall, the gentleman in leading the project from the chemoxy side, taking a side product from a diponitrile synthesis. That stuff there was just being used, was being burnt for its calorific value, but David identified that it could be a good basis of a coalescing agent. Anyone who's a chemist will say, well, Justin, all you have to do is boil that up with a bit of acid or base, and you've got your 2-methyl glutaric acid. Well, you could do, but you'll find that the costs of using all that acid and base and neutralizing at the end of it make this not a good way of doing things. But enzymes love that sort of thing. So we spent about 3-year project on this, moving through from finding the enzyme, testing at 1 litre scale, going to CPI, getting them to do it on a 50 litre scale, and proving it worked, and then working at a much higher scale afterwards. And this is all patented, was patented by Chemoxy. Our sequence is there now. So, and at sort of the the hundreds of grams per litre scale as the way to do it, because often when you see these things, enzymes are used to working in biological systems where they never meet much of their starting material. So one of the challenges in this is to make it go faster and make it go in greater densities. So that is a known problem. I'll skip over this one now because I'm talking too much. So there are interesting things you can talk about in terms of making it better. I think the other thing to do is talk about this other project. This is another one I've done with Paul Race, who's Prof of Biochemistry at Bristol. And this is part of Immortal Manufacturing. We were looking at self-healing behavior again, and Paul knew about this lysyl oxidase enzyme, which takes amino side chains, lysine, and under the right conditions with the right enzyme, there's one called LOX, will produce a cross-link. And you think, well, that's great. There's an opportunity there. That's doing effectively what a lot of the polymer industry wants to do, which is to do some cross-linking. And that's something that we've been doing. And there'll be a paper coming out on that very soon. But some nice pictures just to show what we can do. You can put a whole range of different amines in there, and they will cross-link. It doesn't just have to be lysine cross-links. We've done all sorts of more exciting things, and some pretty typical amines, which are polyamines, which are used by the chemical industry. And you can either make things gel. You can see that Paul's people also use the old dog bones in terms of testing material properties. And actually, one of the more exciting, I'm slightly jealous that his method of self-healing much better than mine. But the heel across his dog bones actually makes the material stronger in some cases than the original material. So scar tissue is actually works very well for healing things. So the next thing is, one of the other aspects we talked about as part of Immortal Manufacturing was data-driven, using data more efficiently. And we had a whole team of people looking at this. And actually, this is one where I think chemistry could do better. And we can look at biology and say, well, biology, you've got it right. If you look about how artificial intelligence is working in structural biology, currently structural biology is being absolutely revolutionized by artificial intelligence. DeepMind, which is that offshoot of Google, which is doing all sorts of bits and pieces, has stepped into the protein structure world and completely revolutionized it. So you can see on the right hand side there a graph which shows a score indicating how good their predictions, or the best prediction has been in a biennial conference for structure prediction, and it's gone from being 30 up to about 90. So there is now a method to take the data, primary sequence data, and give you a really good idea, almost as good as you can obtain by actually physically looking at these structures from X-ray crystal structure. You can get a really, really strong idea of what that three-dimensional structure actually is. And the reason why this works so well is because there's lots of data to train all the artificial intelligence on, and it's all really set out in a very straightforward sort of way. It's easy to access, and it's all in a standard format. And I've had discussions with people in industry about this before, and they go, oh, we've got lots of data. Well, maybe it's not all free, it's not all available, and it's not as big as you think it is. And I think that's really holding us back. So I think if we're going to do this, and one example of this is the polymer industry. We could build better polymers if we knew exactly everything about how polymers work. Okay, but believe me, I don't think there's a great polymer set out there which is in the same straightforward situation as the sort of genome databases, the sort of structural databases that the biologists have. And it's not formatted in a consistent manner. Okay, so there's a task, and to some extent, there's a question about what it's going to tell us anyway. Okay, I'll get to that in a section. As part of the Immortal Manufacturing, one of the things that we did was we actually went to see if we could get our colleagues on this. We're paying at Heriot-Watt. We gave them some databases and said, well, can you predict stuff? If we give you a big database, can you make some predictions? And Wei and Wen-Jun, his student on this, we said, give us some data. So we just blithely handed over a data set and said, no, it's got too many blank spaces in it. I can't deal with that. So eventually, we found a data set. I found 434 polymer pieces of information, and Paul Bingham found 1,441 pieces of data for glasses. And in this publication down here, Wei and Wen-Jun had a look at see what the ability to predict these things are. And now that sounded like big data to us, but it's not. Okay, and actually there was a hell of a lot of manual curation was required to get that. And to be honest, I wasn't really impressed about what it said in terms of what it knows. Okay, so I think we need to think better about this, about if we're going to use, people will talk a lot about AI and impacting on our industry, but we've got to know what we need to get the answers we want. Now, one way around this is by finding more data, and one way we can do this is relying on all the literature. And this is something that I like to think about once in a while. Is sending some cunning AI natural language interpreter into the Royal Society of Chemistry database and coming back with a whole load of information. But that doesn't always work. There's a lovely paper just come out where people have used machine learning on a whole list of every single version of the Suzuki reaction. So the synthetic chemists amongst you know the Suzuki reaction is a lovely reaction. Okay, and that paper, which is linked down there, turns out that AI is completely rubbish. Machine learning is completely rubbish at telling you, well, it's not rubbish, it's no better than your best guess. Okay, because the literature, all people have done in the literature is just pick the most obvious chemicals, and they haven't really looked at the whole range of possibilities. So you look at the literature, and the literature isn't actually going to tell you more than you sort of expected anyway. I recommend you have a look at that paper. It's very interesting. It says most of the reasons why people pick something for Suzuki reactions because they've already got the stuff on the shelf, which is quite an interesting thing. So we need more consistent data sets. I think robotics is the way to do this, or robotic data sets. Tie that in, that would be the way to do it. Lots of people talk about molecular modeling. When you look at lots of these big data sets, they're augmented by molecular modeling, which sort of works. But I always worry that lots of the molecular modeling is informed by the data, so you you getting 2 hits out of the 1 set of data, and I think I'm seeing that we might go down a path there. So yeah, so I think there's a big question to be asked there. I'm going to move on a bit. Okay, so those are the 3 futures: recycling, the reword, biotechnology, giving us some ideas, using data in a way to predict and optimize what we can do. Other things I think we need to get a handle on for the future. Oh man, I'm sure people in the whole room are wincing on this. Can we have some way to talk about interactions between universities and companies really straightforward? I know there was a Lambert toolkit, but that doesn't seem to work. Anytime I want to talk to somebody, you know, it's lawyers at 20 paces every single time. And, you know, can't we just have a single piece of paper where everyone understands what we can do? Because it doesn't exist at the moment, no matter how I say. And, you know, if there's someone here from UKRI, can you do this, please? Can you have a piece of paper that, you know, if you accept your funding, we have to have this NDA or whatever. It would make the whole of UK industry interacting with UK academia much faster if we had an agreed set of legal documentation, which we had to use. First thing. Second thing, and I do this as an academic workforce, okay? Obviously, as an academic, I talk to students, they're lovely. That's one of the reasons I love coming into universities, talking to undergraduates and postgraduates. And one of the things that we are desperate for, they want a job at the end of this. A lot of them will be leaving with quite severe bits of debts, and they come into chemistry degrees because they want to have a chemistry job at the end of it. Tell us what you want in terms of companies. Tell us what you want in terms of their skills. I sit on Heads of Chemistry UK, which is a group which pulls together all the chemists, heads of chemistry in the different universities, and we ask questions like this. So one of the things that's come back is data science. Can your students know a bit more about data science? And, you know, we're working on that. But if there's other things as well, tell us. I mean, in my university, we get lots of people who say they want people who can do pretty significant instrumental analytical chemistry. We teach that as a result. Okay, so interact with the university, please, even if it's just to tell them what sort of people you want as employees. And if you want employees, do talk to a university. You don't have to go through a recruitment agent all the time. You can talk to universities, and I don't know anyone who charges for the privilege. Okay, so please do that. The other thing I should say, and I do this as somebody embedded in a university right now, COVID-19 has affected young people, not because they've been ill, but because a lot of them have not had the whole university experience, okay? So they are not the same sort of people. They have not had exams in the same sort of way. They've not had to mix with people, complete strangers in Freshers Week. They've not had to do as much practicals over the year with fitting in extra practicals to make sure people catch up. So please, when you're doing this, think about people, think about how students might have changed when you're doing your recruitment, because even those people will not be the same. Okay. And then, yeah, I think that's probably, be open to EDI. I should say, just the final thing on it, Ian's popped up. The final thing I'll say about the EDI thing is, the person who did all the manipulation of my data set was a lad who was neurodiverse, okay? And, I said, look, you've got a whole week to do this. Because it's going to be the most boring thing you've got. I've given you the world's biggest Excel spreadsheet. Go find the faults in it. And he came back to me at the end of the day, having done all 400 lines of that thing, saying it was the best day's work he'd ever had in his life. And I said to him, man, you've got a job in data curation. You get into it. Anyway, so do look at various people's skills, because there's some surprising skills out there. Okay, so acknowledgements. So thank you very much to the various people. Matt, who's my colleague here, who I do most of my research at the moment in the sort of chemistry group, and the research group members of mine, past and present. The 2 big research group collaborations I've discussed here, Manufacturing Mortality and Transfire, and the various people's work I've discussed, and those I haven't, thank you very much. The funders whose names are down there I mentioned, and then of course TFI Network Plus for inviting me to give this lecture. Thank you very much.
Thank you very much, Justin. That was a fantastic talk. Okay, do you want to just get out to sharing?
Yeah.
And we'll start. There you go. We can see you now. So yeah, it's time for questions. There's a couple of questions popped up on the chat function. So the first one is from Colin Novamat. The other comment, I think it is, The other problem is working with US companies when protection of IP is a nightmare for smaller companies. Do you have a comment on this particular comment? I think I understand this. I've done this myself in my career. Anytime you are working in a multinational where you have a base in the UK and there's another controlling part of the company elsewhere, it's super problematic. Have you encountered these issues, Justin?
Absolutely. I mean, working with multinationals, I mean, it's all of a sudden you've got to talk to your lawyer, has to talk to their lawyer in Cincinnati. It makes life a lot more difficult. And of course, there's obvious questions there that have to be answered in terms of, if you're going to sue me, whose courts are we going to go in? So, I mean, there are obvious questions about that. But I'd like to think there would be a way around it, because it's for everyone's benefit in terms of finding a way for people to talk as quickly as possible. I mean, well, the two things I'd say is I've been in situations where getting the legals has been longer than the project, okay, and that's to nobody's benefit. And I've also had the situation where I've presented exactly the same legal document to talk to a company that was okay last time, and they've said, no, it's no good. So yes, it is a problem, and more of a problem when you've got overseas companies and multinationals, but it should be soluble. I ask, please make it soluble.
It's problematic. I completely agree. I'm involved in a center with a large number of Japanese corporations, and it is very difficult even to have a discussion by Zoom. It's probably about a month to just get that to happen with NDAs, and then you have sign off at the central. We can't sign off at academic level on a personal basis, so it becomes difficult, and then NDAs get bounced around unnecessarily from the company to the university, and it gets problematic. Anyway, I am just whinging now. So we have another question here from Alan Smith, which is a general question. Do you have anyone in your department interested in alumina chemistry? He's developing some methodology around net zero with using scrap aluminium.
I don't, but this sort of thing is the sort of stuff that Transfire would be interested, which is the consortium would be interested to talk to about, Alan, because it may be something where we can interact, and it may be that the TFI Network Plus might have thoughts about this as well.
Yeah, just as a response to Alan, we can try and help you find somebody. It's part of the job. Transfire and the Network Plus work in different ways. Transfire is a collection of universities that generally work together with a set of companies, whereas we're pretty agnostic. We'll contact any department or any person who's interested in a certain area within the academic community, and if you're a company, we can introduce you, and then we can sit in on the conversations or not. Depends on how you want it to go. So we can you'll have to give us a little while if it's outside of our normal comfort zone, but I would probably start by going to the aluminium Alfed and talking to Jan about it. So that would be my answer to that. And that may end up leading to a submission on a feasibility study to see if it's valid as an idea, which I'm sure it is, but a feasibility study would reinforce that. So perhaps either way is good, Alan. I can see you're there listening. So
I am.
Yeah.
Well, thank you for that.
Yeah, responses to that, if that's okay. I think if you want to take that offline and contact either Justin to go through Transfire ourselves, if you can just post Neil or Debbie post Neil's contact email address, and we set up meetings on a regular basis between ourselves initially, and then often to a company or academic, depending on which way around the collaboration is required.
Okay, well, thank you. Yes, please do that. Yeah.
Just to give you a good example, we ran not very long ago, we ran an intelligent processes workshop, and I was reviewing the grant proposals that came in our last call, which finished on the 1st of April. And it was definitively quoted as there being an outcome from that workshop was this project proposal, because they had met and discussed offline after meeting within the virtually meeting at the workshop, and having a mutual interest in a certain aspect of artificial intelligence, as it was in that case. So another question here from Mark Hudson. Is the UK government's net zero ambition a driver of change at all, or is it largely irrelevant? Oh, that's a mic drop. I think it's a big driver. I think a lot of people are interested in it. A lot of people are driven by it. It focuses the mind and gives you a target, 2050. You know, and it is. I think it's an important thing. That's my opinion. What about you, Justin? What do you think?
Yeah, I would agree. It's something we have to do. It's a case of we've got to do it. We've got to find a way to agree on a timescale for everybody to do it. Some people will want to work faster than that, and I would applaud people working faster and with maybe with slightly different focus. But yeah, I'm all on board for net zero. I think, you know, you've got to do it.
Yeah, I think it's whether it's the actual government rhetoric is driving it, or is it just? I think without the government rhetoric, it wouldn't be such an active thing. I think there's a symbiotic relationship between the government rhetoric and the actions that are being taken, and one is priming the other, I think. So I think it's a good thing in general, and we should applaud all governments around the world for doing ambitious targets. Whether we think they're ambitious enough is another matter, but we should be, you know, happy that they've actually recognized this and are driving it top down, whilst we drive it from bottom up, which is what the research does. Okay, I can't see any more in the chat function there, but I have a comment to make and a question, I guess, Justin.
Yeah.
I noticed you've been working with Paul about the glasses and setting up databases. I'm probably more ceramics than Paul Bingham is, because he's more towards the glass. I know he does some ceramics. And our big issue with computational work, and just, you know, trying to get functionality out of by intelligent design by computing power is dopants, and microstructure.
Yeah.
So we can change from a semiconductor to an insulator with about 0.5% dopant very easily in oxide-based ceramics. We can modify the functionalities massively by incredibly small amounts. And also, of course, if you then move away from to mechanical properties, wear resistance, and then you're really talking about the strength of grain boundaries in many instances, and segregation to grain boundaries affects the strength hugely. So how do then these artificial intelligence systems, which are going to work through lots and lots of permutations and combinations, I'm not sure how it deals with that. And I think they're wonderful at inventing base structures, crystal structures, which should have a property if they can be fabricated. But going from something which has a predicted property to a lump of ceramic that has that property reproducibly is tremendously difficult. Yeah.
Okay, so that's very true. I would agree with when you've got something where it's very difficult to find lots of different analogs or slightly different things to get, you know, to get a prediction, because everything is so wildly different. But I have to say, I think AI has a way there, because AI is being used to speed up computational work. Okay, so you know, I've been working with somebody here who is able to model sort of polymer systems, because, you know, what you can do is you can, instead of modeling every atom, you can model a subunit.
Yeah.
And from that subunit, you can say how that subunit actually interacts with each other, and those actions or reactions or interactions of the subunit can be how it interacts in different ways can be accelerated by AI. So AI acceleration of molecular modeling is probably the way to do that. And actually very large simulations can happen these days with a large enough computer, which are more on the material scale than on the molecule scale. And I think that's the way forward in that sort of stuff. And I would like to see how it would actually work, you know, as you say, across grain boundaries. I mean, we've been looking at, you know, if you break a system and push it back together, as I said before, posh melting, or is it actually some sort of self-healing, you know, looking at that on a much larger scale than just like, oh, this atom talking to this atom. I think that's interesting, and AI has a way to accelerate that.
I think you're right. I think it has got its place, and we need to push it, but it's not there yet, is probably what I'm saying in terms of predictive properties, from my perspective anyway, and this is a personal view. It is not the view of the Transforming Foundation Industries Network Plus. So there's a couple more questions before we complete. We're coming to the end now. There's a comment from Michael Juice. Should chemical sector aim to avoid all of its emissions by 2050 through innovation in materials and recycling? Do you think that's viable, or do we think we need to go to carbon capture and storage? I think is Michael's question.
I think it's going to have to be a bit of everything, to be honest. I think it's going to be difficult to just go in one pot. I think we've got to try everything, because, to be honest, we don't know how efficient half of these things are, and you know, there's at the time, you know, there's a strict time limit which we've got to work to. So I'm all for trying all particular things. Yeah. And
yeah, my comment would be that we end up in a situation where the public generally likes one-point answers or one-point solutions, where it's not that. It's a multi-point solution. It's a holistic response. And I did a presentation recently showing that if we start now with some relatively small things, they have great importance by 2050 in terms of carbon abatement. And I think that's the message: is we need to do everything. And saying one solution to it all is probably a mistake, in my view. And again, that's my personal opinion expressed, not from the Transforming Foundation Industries Network Plus. I have to put that rider in all the time. So we have Stephen Welburn, Energy Nest are looking into how a thermal storage system can help reduce energy consumption in chemical production. Shifting waste from decoking reactor to preheating furnaces. Have you come across this? Justin, you have a comment on this?
Yeah, so this is definitely something I'm quite interested in learning more about. My background as a sort of synthetic chemist means I don't really understand as yet how you can move heat from one thing to another. It's a lot more subtle than I think it probably is. So, you know, one of the things that I have to learn as part of my role here is in Transfire is to find out how that works. So I'm quite interested in doing that, because, as I said, atoms versus joules, it's going to have to be both. We're going to have to conserve atoms. We're going to have to conserve energy, and there is clearly waste energy. How it's done is going to be very important.
Steve has just popped up. Do you have a follow-on point there?
Yeah, no, I'd just like to follow up that discussion, Justin, because yes, what we're doing is pretty innovative. We've got university completing a study in about 4 weeks' time. We've identified a number of opportunities where we can capture heat at one point in time and deliver back at another point in time in hours later. So it's truly a change in how we're going to manage waste heat.
Okay, it sounds very interesting, Steve. I'll contact you offline.
Thank you.
I think that's probably a good notion. There's one point for me. Do you see a future of doping to induce reactivity in recycled ceramic waste? I would have to know the nature of the ceramic waste in question, because ceramic wastes are pretty broad. They can vary from multi-layer ceramic capacitor wastage, which is a pretty narrow, high-value product, to tile wastage, which is by tile production standards, it's a high-value product, but on the big scheme of waste, it's a relatively low-value thing. So I couldn't answer that question, Sam, without knowing more about the type of ceramic waste. Thank Thank you, Justin. Thank you for that. I learned a lot. It's a long time since I've seen so much organic chemistry, I have to say. It's not my thing, but yeah, some of it was quite familiar, so thank you for that. And thank you, everybody, for joining in. I thought it was a pretty good discussion by the end. And I hope people get something out of this. There seems to have been a few contacts being made. Really, you know, that is the main purpose of this kind of seminar and the workshops that we put on with the Network Plus. We want to get people talking to each other and perhaps following up with some work with Transfire through Justin, or maybe through a Network Plus through Justin, or anybody else who is a viable collaborator, either academic or industrial. I think this is the vital thing. Okay, I'm going to say goodbye to everybody and thank Justin again.